Right, time to go through covalent bonding and naming. So let's review covalent bonds. What happens to valence electrons in a covalent bond? Well, those valence electrons are shared. So you can see here, this fluorine has one unpaired electron. A second fluorine would also have one unpaired electron. So they share them in between them. And voila, all the electrons have pairs. Here's several different views of looking at methane, which is carbon with 4 hydrogens surrounding it. And you can see carbon contributes 4 valence electrons, and each hydrogen brings over 1, resulting in all of the electrons being paired, shared between them. Covalent bonds can be nonpolar. That means the electrons are shared equally. And this often forms between atoms of the same element. So all those Brinkelhoff elements like hydrogen, chlorine, oxygen, and so on. Now, if you're using electronegativity difference, the closer to 0 the difference is, the more nonpolar. Because whatever hydrogen's number is, 2.2, when you subtract 2.2 minus 2.2, you're going to get 0. Okay, so as close to 0, that's nonpolar. But covalent bonds can also be polar. So here the electrons are shared unequally. So the electrons are pulled closer to the atom with higher electronegativity. And this results in partial charges. So here's water. Since oxygen has higher electronegativity, the electrons are pulled closer to oxygen. So oxygen is partially negative, and the hydrogens will be partially positive. So if you're using electronegativity difference here, it's going to be, from around 0.5-ish up to around 1.7. But the important thing to know when you're doing electronegativity difference, the bigger the difference, the more polar. The smaller the difference, the less polar. Okay. Here's another example of a polar compound, and you can see the electrons are shared unequally. They tend to be around atom A and not B. Here's another example of water. You can see the partial positive and partial negative charges. Now, covalent compounds are called molecular compounds. They are poor conductors. They are formed between nonmetals, and covalent compounds or molecular compounds can be solids, liquids, and gases. When covalent bonds are nonpolar, the molecule is going to be nonpolar. So if the electrons were shared equally in the bond, then the molecule ends up being nonpolar. In this case, that means there's symmetry. So the electrons are shared equally. There's no uneven charge distribution. When the bonds are polar, it's a little bit more complicated, or if you at least have one bond that's polar. So the molecule overall can be polar or nonpolar. So how do you figure it out? Well, you look for symmetry. If there's symmetry of the polar bonds, the charge is distributed equally, then the molecule itself is nonpolar. So it would be a nonpolar molecule with polar bonds. If there is no symmetry, then the charge is distributed unequally, and then the molecule is polar. So the molecule is polar with polar bonds. So here are some examples. Here we could see non-polar compounds where the charge is going to be distributed equally. And then we have polar over here where we have unequal distribution of charge, and it results in the molecule being polar. So for example, for water, all of the negative hangs out up here, all the positive down here. That's not symmetry for charge distribution. Same with this ammonia molecule, okay? Here's a few more examples where you can see the distribution. When the molecule is polar, we have polar bonds. The molecule can be non-polar, right? And these molecules are also nonpolar because the charge is distributed equally. Here are some more examples of polar versus nonpolar molecules. When we have polar molecules, the charge is distributed unequally. When we have nonpolar molecules, we have the charge distributed equally. So let's look at some examples. What would this molecule be? Well, you can tell there are polar bonds, right? Because we have partial positives and partial negatives. Is it distributed equally? Yes, it is. So it is nonpolar. What about this molecule? This one you should know because it's very common. Yeah, water is polar. What about this one? What would this molecule be? Yeah, nonpolar. What about this molecule? Yes, polar, unequal charge distribution. The charge is pulled closer to fluorine. What about this molecule? What would it be? Well, first, I do see partial negatives and partial positives, so you have to think, is it distributed equally? Yes, it is. It is nonpolar. What about this molecule? It is nonpolar. The charge is pulled closer, those electrons, to oxygen, but it's distributed equally. And what about this molecule? Well, this one is polar. Why? Because look, this F is going to pull harder, and that's not the same as what is on all the other sides of carbon. So what about this one? Yeah, this is nonpolar, okay? Now, let's go to naming. So, when we are naming covalent compounds, we have to use prefixes. Fun fact, you have to remember them. You just have to know them. Now, the good news is you don't have to know that many, but 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa. I don't usually see more than that, but the rest, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. These are not on your reference table. You just have to be able to pull them from your brain. Now, this is for IUPAC rules for naming, which means the International Union for Pure and Applied Chemistry, blah, blah, blah. That just means the way we name stuff, okay? So the rules for naming covalent compounds are like the easiest. So the first element uses its name. If it's oxygen, it's oxygen. If it's carbon, it's carbon. If it's hydrogen, it's hydrogen. The second element uses IDE, so its ending changes to IDE. That sounds like the naming rules we did before. So oxygen becomes oxide, hydrogen becomes hydride, sulfur becomes sulfide. And both elements use a prefix. So if there's 2 oxygens, it's di. If it's 3 oxygens, it's tri. Okay? Now, of course, it couldn't be quite that simple because there's an exception. We don't use mono for the first element. So if there's 1 carbon first, we just say carbon. We don't say monocarbon. But if the second element has 1, we have to use it. We say mono. So when we get to some examples, it'll make more sense. All right, so here's this one. Okay, so let's name it. What is this first element? This first element is called what? Carbon, right? How many carbons do you see? 1. All right, what is the second element? Oxygen, but we change it to oxide, right? And how many oxygens do you see? 2. What is the prefix for 2? So we say di. So the whole name is carbon dioxide. You already knew that though, right? Remember, we don't use mono for the first element. Let's try another one. All right, so let's look. Nitrogen, right? 2 of them. Oxygen becomes oxide, 5 of them. So what do you think the name is? Dinitrogen pentoxide. Now, we don't usually write pentoxide because that sounds a little awkward, but if you had to write one and you wrote that, like, it's okay. Okay, try this one. 1 sulfur, 6 fluorines. What do we do with the name for this one? What do we do with the name for this one? Did you get this? Sulfur hexafluoride. 1 sulfur, but remember, we don't add mono for the first element, and fluoride because the second element ends in IDE, and hexa because there were 6. Now this is water, right? But what would the name of water be following the covalent naming rules? You have to go step by step. This is hydrogen, how many? This is oxygen, how many? So did you get this? Dihydrogen monoxide, right? So we use mono for the second one. The only time we don't use mono is when it's the first one, okay? Now let's try the reverse. So here is disulfur dichloride. This is super easy. Like, this should never be wrong. So sulfur is what? S. Chloride is from chlorine, right? Di means how many? 2. Di means how many? 2. Voila. Let's try another one. Phosphorus is what? P. Chloride is what? Cl. There's no number here. There's no prefix, right? So I leave it alone. And penta is 5. Okay. Try this one. Phosphorus, fluoride, di, penta. All right. Try this one. Nitrogen, oxide, no number, and mono. That's it. Voila. Covalent naming, easy peasy.